Good evening, everyone. I hope uh, the voice is audible. Uh, and today we are in the fifth week, and we are going to discuss some problems related to the uh, lectures which were happened during the course of the week five. And uh, firstly, my name is Syed Shabir Ahmad. I am a PMRF scholar from IIT Madras Department of Applied Mechanics and Biomedical Engineering. So, as you guys all know, this course is taught by Professor K. Ramesh, and he also happens to be from the same department as of me. And I hope uh, you are enjoying the course. If you have any discussions or questions related to the course, uh, we have a discussion forum through which you can ask directly uh, to the uh, other TAs of the course who can also answer your questions whenever you have doubts. You can see on the top of the NPTEL uh, in portal of NPTEL in that course. You can see on the top ask a question. There will be a tab, so you can click on and ask the questions. Subsequently, you can ask it here in the class. So but these sessions are primarily indicated as to help you solve the assignment problems which for the uh, respective weeks which we are going to discuss. So last week in the week five, uh, there were three lectures which were basically based on the state of strain, and the other lecture was on measurement of strain. And we had a lecture on the tensile test. So I hope you have watched the lectures, and uh, there are different aspects whichever you have come across. So let's see some questions which were related to this thing which we have discussed. Firstly, in the lecture, professor discussed about state of strain. So when we can take basically whenever we take a coordinate system, it can be either be a polar coordinate system and or it can be a uh, rectangular coordinate system. So we have rectangular coordinate system, and also when we have circular or some kind of elliptical shapes, we also take polar coordinate system. So hi, Kamaluddin, can you hear me, right? I hope you can hear me. You can hear me. You can turn on your mic and say, you can write in the chat or you can give me a thumbs up. If you have any problem listening to me, you can type in the chat box or let me know. Just okay. In a rectangular coordinate system, we have three axes basically, three or you can say three directions, x, y, and z axis. So independent axis, and the strain, as we all know, we have taken it as dou u by dou y, plan y by as dou v, dou u by dou x, dou v by dou y, plan the dou as dou w. So this is basically, let's say only we have a two-dimensional coordinates system, two dimensions. Because in this course we mainly deal with this two dimensions. So then we have epsilon xy as half into dou u by dou y plus dou v by dou x. So this is the two. These are the two normal strains and one shear strain. Or this can also be written as gamma x by when we go to the polar coordinate system, we have two directions basically. One is the radial direction and one is the circumferential uh, direction. So r and theta. So the radial strain can be directly given as dou u by dou r, and we have the uh, circumferential strain. Generally, what you can say in circumferential direction, if I say the displacement is v, then dou u by dou theta. But because this is measuring uh, normal stress, not this is the shear normal strain, not the shear strain. That's why we have dou u by dou r theta, an extra term plus u by r. Also, we have this u by r. So we have this slight extra terms. I hope you have watched the lecture in which we have a take. Professor has taken an element and shown how we get this normal strain in radial and normal strain in circumferential direction, and then we have this. Then we have the shear strain in uh, radial direction, shear strain in polar coordinates, which is gamma r theta. So this has to be dou u by dou theta, 1 by r into dou u by dou theta, plus dou v by dou r and minus v by r. So here you can see here this is a this term is extra and r comes extra. Whenever we have theta in the denominator, remember that we will get this r as an extra term. Here also we have this term is similar to the polar coordinate. This term is similar to this but we have r extra, and this one is extra here. This term is extra minus p by r. So these are the differences when we denote a state of strain. State of strain means whatever the strains in uh, independent coordinates present uh, in the coordinates strain, what are the independent strain components present, that denotes the state of strain. I know we have a matrix like this. So in this, it is a symmetric matrix. That's why we have only three strains. So 2 by 2 matrix, uh, epsilon xx, epsilon xy, epsilon xy, epsilon xy is same. I hope you know the. It is similar to the um, equality of cross shear. So strains are also equal. So in the similar way, we have here also we have epsilon r, epsilon r, gamma theta. So and also epsilon uh, theta or theta whatever. So this is how state of strain is denoted in a rectangular coordinate system and a polar coordinate system. And this diagram, you can see if you have watched the lecture. This is this shows an experimental procedure called digital image correlation. So, or this is, you can say simply DIC. So, whenever we have one camera and whenever we have only one camera, that is called as a 2D DAC, because it doesn't give information about out of plane deformations or displacements, whatever. So only one camera. 2D DIC has only one camera. But here, since we have two cameras, that is called as 3D DIC, because this also gives us what is happening in the lateral direction, how the material or the specimen is deformed. So 3D DIC and 2D DIC. When we have two cameras that are present, then it is called a 3D DIC. So this specimen, whatever we take in this experiment, we uh, paint this with a white background, and there are speckles like this, black dots, if you can, black dots. The specimen is painted like this, and then the load or the load is applied on the specimen like this. And before, so what we do is we take the undeformed image, and then as you will apply load, and as you apply load throughout the load application, as you increase throughout the uh, experimental procedure, we are continuously taking images at a very high speed, uh, at a very high rate. So lot of images are taken, and then you compare this initial image, which is uh, not deformed the image of the specimen, and then as you as the load is applied, this material or this specimen deforms, and you can see there will be uh, change in this images due, because the deformation is happening, the speckles are also moving away or towards each other due to the deformation. So this thing is processed in the computer, and we get the full field strain measurements. Whenever I say full field, it gives the information about whole of the specimen, which how much ever it is capturing. So whenever we use this 3D DIC, this is the uh, advantage of this three dimensional image correlation, which is also non-contact way of measuring the strain, and also getting the full field strain. And also 3D DIC gives us out of plane displacements and as well as the in plane displacements. So here in 3D DIC we measure the displacements and also the gradients. So as you all know, gradients are also very important. Using the gradients, we can take using the displacement gradient. We can convert. Uh, we can divide it into or decompose into two parts, which is a rotational tensor and also a strain tensor. So that is how we are going to get the displacements and also the displacement gradient. From that displacement gradient, we are going to get the rotational tensor and the strain tensor of the whole field. Just a minute. And if you see this image, so this in this also, uh, this is an experimental procedure which we are conducting, and uh, there are, like, as you can see, there is a computer, and which we have two cameras and two light source which illuminate the specimen. So and the other side you can see uh, a polarizer and analyzer, and uh, you have a light source, and then you are taking the reflections after the material reflects the light, after the specimen reflects the light. So as we have seen from the above discussion which we have discussed, this part uh, of the on this part of the specimen we are doing 3D DIC, 3D digital image correlation. Just a second. So this part we are doing 3D 3D DIC, and this part here, this is reflection photoelasticity. Here, as we have discussed in the real sections uh, also, so earlier picture also, here we have to, on this side of the specimen, we have to paint the specimen and also with a white coat along with speckles so that we get the deformation uh, which is happening due to the applied load on the specimen. And here on this side, where we are doing the reflection spectro photoelasticity uh, experiment, because this is a, if this is a, assuming that this specimen is an opaque, that means which doesn't allow low light to pass through it. So we take a photoelastic coating of some material such that whenever after we apply the coating, we apply light through which passes through the polarizer, and then you get the reflection of light which passes through the analyzer and gives you a nice photoelasticity picture which has fringes on the specimen due to the applied load, which induces the stresses in the material. So these are two specimens. These are two experiments. Both of them, one is basically direct strain uh, measuring procedure, which is 3D DIC, and reflection photoelasticity is basically we are measuring the stresses, and then we go to using that we calculate the strains of that. So when we go to the next week, probably I guess. So we learned till now whatever we have learned in this course. So uh, we have separately first we have taken up the concepts related to stress, uh, how it is uh, how it is behaving, and what are the different components of it, and how we get stress as a tensor, or as how we describe stress as a state which is a tensor, not a vector, and how we go about finding the principal stresses and also the maximum shear stress. Then we have discussed what is strain, uh, and how strain is the concepts related to strain are defined, and then what is the state of strain in polar as well as rectangular coordinates, and then how we are going to measure strain. So measuring strain using like if you want to measure uh, point strain, we use strain waves, and if you want to get the fulfilled measurements, like you use this photoelastic reflective photoelasticity, and also you have we have this image correlation, and in order to measure stress, there is only one way to measure the stress is using the photoelasticity, which we have discussed. Our professor has discussed in the class lectures, last week lecture, and there are like different concepts like how you relate the uh, properties, photoelastic properties with the mechanical properties. Different things have been discussed in the last class, and this next we will go to this part, and we have a delta rosette. So this uh, so in order to get the state of strain, state of strain, we should have at least least three strain gauges. So using the measurements on three strain gauges, we can get the state of strain. State of strain is nothing but the matrix, here 2 by 2 matrix, because this I'm talking about the two-dimensional thing. So because a strain gauge will, a strain gauge, a single strain gauge will only give us component of strain in axial, axial or length direction, length of the strain gauge along that direction. Like here, like this, we have a strain gauge. There are different coils, and you have the connections which are separate. This is the length of the strain gauge, and strain gauge will give you axial strain in this direction. So it is not possible to determine what is the state of is uh, perpendicular direction, uh, uh, perpendicular direction, two perpendicular directions, and also the shear strain. It is not possible to give with a single strain gauge. So it gives only the axial strain in the length direction of the strain gauge. So here we have three strain gauges. It will give strain in this direction. It will give strain uh, in this direction, or opposite, whatever it is, and it will give strain in this direction. So that's why we need at least three strain gauges to measure the to get the state of strain at a point. So these strain gauges are very small, so you apply it at a small area. So uh, like obviously we say that we measure the state of strain at a point, but this is not exactly at a point, but at a small area at which this rosette is applied on the specimen. So there are different kinds of rosettes which can like uh, which are available, like a delta rosette, star rosette, and also a rectangular rosette. So whatever, like we have uh, different depending upon the procedure which you are doing, and depending upon the experiment, the specimen, whatever. So different rosettes are used uh, to do this to get the state of strain at a point. So here in this question, uh, a delta rosette, uh, uh, it is given that uh, epsilon A is 300 microstrains, and epsilon B is 400 microstrain, and epsilon C is 500 microstrain. So we have got these measurements, okay, of the strain gauges, strains along these directions of the strain gauges which we have applied. So we now want the state of strain, which in the rectangular coordinate system, which is this epsilon xx, epsilon y, xy, and epsilon xy, and epsilon uh, y. So as you know, gamma xy is uh, 2 of gamma xy is sorry, epsilon xy is it's like that. So so we have strains in A direction, B direction, C direction, which are not actually rectangular or to each other, and they are like not perpendicular to each other. So whenever we have like strains given in different direction, uh, let's say you have strains given in xy, xx, xy and gamma xy direction. You know these three, but you want to get the strain along any random direction which is at angle theta uh, from the uh, x-axis or the uh, strain in x direction, which is theta. Like you have x, y, and let's say this is some normal, and you want to measure the, you know this, you know this, and you know this, and you also know gamma xy, but you want to measure the strain in this normal direction, which is making an angle with as theta. Then we have studied the strain transformation laws, which give us epsilon n can be given as epsilon xx cos square theta plus epsilon yy sin square theta plus gamma xy sin theta cos theta. So using this law, strain transformation law, we basically get this known strains in x, y, and shear strain gamma xy to get the strain in the along the uh, along a normal direction, which is making an angle theta with the x-axis. So this is the strain transformation law. Okay, so we know uh, trigonometric identities and like trigonometric trigonometric formula, which whatever we have studied in the uh, grade 9, 10, or like plus 2 plus 1 plus 2. So cos square theta can be like written as uh, cos 2 theta is equals to 2 square theta minus 1. So uh, I just want to eliminate this squares here. So using those trigonometric properties or identities or formula, whatever, uh, we can write this thing as 1 by 2 epsilon xx plus epsilon yy plus 1 by 2 epsilon xx minus epsilon yy cos theta, cos 2 theta, and plus gamma xy by 2 sin 2. I hope you know this. Let's say cos 2 theta can be written as 2 cos square theta minus 1. So if I want cos square theta from this, cos 2 theta minus 1. Okay. Substitute this. Similarly, cos 2 theta can also be written as 1 minus 2 sin square theta. If I want sin square theta 1 minus cos 2 theta. So if I substitute this, instead of this sin 2 theta cos 2 theta, if I multiply and divide by 2, I'll get 2 sin theta cos theta. Sin 2 theta is equal to 2 sin theta cos theta. So replacing sin 2 theta plus cos theta. That's how I get this. So here, as you can see in this rosette, we have if I take three axes uh, like this, this, this is x, this is y. So as you can see, A is making an angle. Strain rosette A is making an angle 0 degrees theta A. It is making an angle of 0 degrees with the x-axis. Then you can see B, it is making an angle 60 degrees. 60 degrees. B is making an angle of 60 degrees. Then you can see the strain gauge C. Uh, the direction of strain gauge C is making normal direction of this is making an angle 180 minus 60, which is basically 120 degrees with the x-axis. So, so first, let's say normal direction in here can be given as 1 by 2 epsilon xx plus yy 1 by 2 epsilon xx epsilon yy. So theta is 0 here. So cos 2 theta is also cos 0 you will get. Cos 0 is 1 and sin 2 theta is 0. So that will be 0. So epsilon x direct epsilon a you will be equal to epsilon x. This is the first equation you can see. Then we take the normal strain in the direction B. So in this we have theta is 60 degrees. So 1 by epsilon xx plus epsilon yy plus 1 by 2 epsilon xx minus epsilon yy cos 2 theta plus gamma. So theta is 60 degrees. I will replace that with 60 degrees plus gamma x dot, right? Sin 2 theta. 2 into 60, I will just directly write the constant. So here we will get epsilon xx plus epsilon yy plus 2 epsilon xx minus epsilon yy. So cos 120 you can directly write as sin 30 or cos 120, which is 1 by 2 minus 1 by 2 cos Cos is negative there. Cos, let's write it as minus 1. We have sin 120, that is root 3 by 2. So you can take this as equation, and then we have the strain in C direction, normal strain in C direction, where theta is 120 degrees. Epsilon xx plus epsilon y as 1 by 2 epsilon xx minus epsilon y cos 2 into 120 gamma xy by 2 sin, and just write it as 122 into 240. So we get epsilon xx plus epsilon y 1 by 2 into 1 xx minus epsilon y, right? So cos 240 which is sin 180 plus 60, cos 240 cos 60 which is equal to cos 60, it is 1 by 2 minus 1 by 2 cos 180 plus 60 is cos minus cos 60. And similarly, we have gamma xy sin 240 is sin 180 plus 60, sin 60 which is I think minus root 3 by 2. Yeah, minus root 3 by 2. So here we know three equations, and in which the knowns are epsilon A, knowns are epsilon A, epsilon B, and epsilon C. So epsilon A, epsilon B are measured and taken from the strain gains. So we have to find the state of strain, which is epsilon xx, epsilon y, and epsilon gamma xy. So the unknowns are epsilon xx, epsilon y, and epsilon sorry, gamma xy, gamma xy. So we have three equations and three unknowns. So using the uh, substitutions or whatever it is, we can interchange, we can use these three equations to find out the values of epsilon xx, epsilon y, and gamma xy. I won't do the all the stuff, calculation stuff. I'll just directly write down. First, epsilon xx, we have already got that epsilon xx is equals to strain in x direction is equal to the strain in the uh, strain gauge A. So that we have already got, and epsilon yy, which is which will be equal to 1 by 3 2 into epsilon b plus epsilon c minus epsilon a. So this is by simplifying all the three equations which we have got. And then we have the shear strain gamma xy will be equal to 2 by root 3 epsilon v minus epsilon c. So I've got values. First, we know epsilon xx is equals to 300 microstrains, I guess. Yeah, 300 microstrains. Now, let's calculate epsilon yy. I know 2 into 400 plus 500 minus 300. I'll do this. I will get 500 microstrains. So epsilon yy is 500 microstrains. Got this. And then I have gamma xy 2 by root 3 epsilon b is 400 minus epsilon c is 500. So we have got do the calculation in a calculator. This as minus 115.47 microstrain. So I know epsilon xx and epsilon xy, which is gamma xy by 2, epsilon y. So this is similar. I don't need to write it. So using the value of the strain gauges, strains from the strain gauges in the delta rosette, we have got the state of strain at this point, at the point at which the strain rosette was attached on the station. So this is how we take the calculations of the strain rosette and of the this is how we do the calculations using the values of strains from the strain rosette to get the state of strain at a point. Next, we will do this question. I'll just copy it. So this is a stress strain curve which is given for a tensile test. Uh, what is happening? This is a sorry for the disturbance. I don't know what the pencil is not responding. I guess. Oh, I have lost everything. That's everything. Yeah. Okay, fine. Whatever. I hope if you are watching on the video, could be frustrating, you can just forward to the point where I'm starting the explanation. So, um, okay, I'll just or hi Devashish, can you hear me? If you have any problem in the voice,
Hello.
yeah, can you hear me?
Hello.
Hello, hi Devashish, can you hear me?
Now okay, sir. Now, yes, yes, yes.
Oh, okay, okay,
Yes, now I'm here. You are audible now.
okay.
Sorry for
So,
the delay because I.
yeah, it's okay, it's fine, completely fine. I can understand. Yeah. So we are just, I'm just discussing this problem. So we'll start, and again, in the end, I'll discuss whatever I have discussed till now. So I hope you stay along.
Sure, sure, sure.
Yeah.
Sure, sure, sure.
So have you watched? I hope you have watched this lectures of this 15th week
This
related to,
of last week. Yes, yes, I already seen.
yeah, state of strain, and one lecture is on measurement of strain, and the other lecture is on tensile test. So basically, so this in this question, I am just drawing a curve like this. This is a stress strain curve for an experiment. Basically, whenever you see this kind of curve, this is generally for a mild steel bar. This kind of curve you can see whenever you do an experiment. So there are points given, like different points A, B, C, D, and E. So in this curve, as you can see, whenever you go from point O to point A, as you gradually increase the stress, uh, this you can see uh, there is a linear variation. Linear variation in the sense this line is a straight line. So as you increase the strain, the stress is also increasing linearly with respect to the strain. So that's why here to here you can see this is this point, the point at the point A, up to which this strain and stress relationship is linear. This point is called as proportionality limit. Proportionality limit because it is linearly or proportionally varying with respect to the strain. Stress is varying with respect to the strain. And there will be another point like A to B will be slightly linear. Let's say I'll write it as uh, some point, let's say gamma. I'm just giving a different Greek alphabet for this. Here, A to gamma, it will not be linear, but whatever the stress or the strain up to which you apply, if you release the strain, it comes back to the original position. The material regains its shape without any deformation. So that's why this gamma point can be called as an elastic limit. So elastic limit, like if you have a body, you apply a strain or a deformation. If it comes back totally to its original condition without any residual deformation, like a rubber band, you can say, like you can elongate it and it comes back to its original shape. that up to this point, this phenomena happens, that it comes back. There will be no residual deformation. But after this point, elastic limit point, there will be a point B, which is called as a up yield point. Here in mild steel, we can see
The
a
screen is
what happened.
sometimes screen is not visible. That is blank fully.
This what I am writing.
Now visible.
That's
Okay.
is it visible? Yeah. Okay.
Yes. Yes.
Yeah. So to this point gamma, the material will be the mild steel bar will have elastic properties, which means like if you release the load, it will come back. The material or the specimen will come back to its original shape without any residual deformation. So at point B, we will have the yield point. So yield point, after the yield point, what happens is that the material will start deforming like a plastic material. So whenever uh, you go beyond this point, beyond the yield point, and you release the stress, there will be some deformation which will be remaining in the material. So let's say if you if you go till this point and you release the stress, you release the strain, it will come back. It will come back to this position. It will come back in this direction. There you will have a residual strain. This is the residual strain when you release it from this point. So there will be some plastic deformation in the specimen when we go beyond the yield point. So this region B to D is called as a strain hardening zone, because here you can see the slope is decreasing, and strain is actually increasing in a higher greater way with respect to the strain. So for a very less strain, less stress applied, there is huge strain. So that's why it is called as a strain hardening zone. So strain hardening zone, there will be a lot of inter subatomic or molecular level uh, uh, deformations happening due to that structure of internal structure of the material changes, and this happens in this one. And this point, the D point, is called as the ultimate stress point, because this is the highest ultimate stress. This is the highest stress when we do the experiment on the specimen. So, and then we have finally the fracture stress or the failure point at which the material fails. So, this from this you can see there is a slight drop in stress from ultimate stress to fracture stress, and this region is called as necking zone. So, if you have a material like this, it will due to the applied load, there will be like uh, necking deformation will happen, like there will be a uh, reduction in diameter or the dimension, and then the material after this necking happens, the material will fail. So this is called the necking zone. So uh, what else? Okay, the ultimate stress point. Yeah. So here uh, he has given that load at proportionality limit is 12.5 kilonewton. So at this point, at point A, load is given as 12.5 kilonewton. So remember, this is actually stress. This is actually load, not the stress. So the specimen on which the experiment was conducted is a dog bone sample. So whenever you do a tensile stress, you take this kind of specimen. it is called as a dog bone sample or a dog bone specimen because it simply resembles like a dog bone. So here you will hold the material. Here you will use this both ends to hold to the universal testing machine which you have. Whatever the testing machine you use, this two ends will be used to hold, and whatever this length is called as the gauge length, and this is mainly affected by the experiment which we conduct. This is called as the gauge length, and also you can see we reduce the thickness gradually uh, from the wide ends which we have, so that there is no stress concentration. These are called fillets. So and then using after fixing these both ends, we apply the load, and material will fail like this due to the tensile load. Something like due to making, material will fail. He has given, there are some standards for this experiment, like different societies, like there is one American society, ASTM, which gives the standards uh, because there should be some consistency whenever we do testing on different materials, like uh, it's not like because this cross section or what. Okay, screen is not visible. Is it now visible?
Yes, sir. Okay now.
Okay. So yeah, so we have different societies, like different standards. So the thing is, when we change the specimen type or gauge length, or let's say cross section of the specimen, there will be some variations in the values of the stresses which we obtain. So in order to maintain that consistency, we take uh, specimen which is prescribed by the society, and every industry or the every individual who manufactures the material or some specimen should use these standards and test uh, the material or the by making this specimen, and he has to give the values to uh, the buyer or someone, whoever is buying those. He has to give the strength of the material uh, according to the standards, using the specimen standards set by the societies. So here they have given that this uh, gauge length has a diameter of 12 mm, and gauge length is basically 50 mm. Okay, and extension at load of extension at load of 8.8 kilonewton, which is below the elastic limit. Extension is given as 0.05015 mm. So it means that up to 8.8 kilonewton. So the thing is, we apply the load gradually from zero to we gradually increase the load, and we test it. We don't apply a sudden load. So when we apply sudden load, we don't get this kind of stress strain curve. It will directly start from here. So that is a different other thing, like that can be you can say impact testing, that kind of thing. Here this is tensile test. We apply it as a gradual load, so it load is gradually increased. So till the load is applied to 8.8 kilonewton, this is the extension, and load at D, point D, which is the ultimate stress point, is given as 20 kilonewton, and load at E, the failure point. I don't know what is happening today. I'm sorry. Is it visible now?
No, sir, not now.
Okay. I'll just connect the Wi-Fi to my laptop. Yeah. Is it visible?
Yes, now visible.
Okay.
Yes.
Yes. So load at ultimate stress is given as 20 kilonewton, and then load at E point, which is the failure point, is given as uh, 19 kilonewton. So as I said, there is a drop in stress, so there is also a drop in load at the failure point. And total elongation of the rod till the failure, total elongation is given as 3.5 mm. And and yeah, that's it. So first thing is, uh, in this, let's see what is the uh, stress, ultimate stress, uh, ultimate stress in the specimen during the test. So in this ultimate stress, let's say uh, we can, stress is basically load by cross section area. So load at the ultimate stress point is uh, 20 kilonewton, which is D, and we have the area 5 by 4 T square. So T is basically we have 12 mm. So if I get this 20 by 5 by 4 T square, because this is in kilonewton, I'll just take 10 cube. I'll get 166.838 Newton per mm square, or this can also be called as megapascal. So 168, 176.838. So this is the stress at point D, at, or you can say ultimate stress. This is the ultimate stress. Now we have to find out the Young's modulus. Young's modulus for the material of this specimen. So here I'll just draw. So Young's modulus is basically, we have this Young's modulus is up to this point, whatever the slope of this straight line is there, that is called as the Young's modulus. Up to the proportionality limit, whatever we get the slope of this straight line, that we call it as the Young's modulus. So here we have got uh, uh, okay. Yes. You can hear me, right?
Yes, sir.
Okay. Now is the screen visible?
No, sir.
No. Okay.
No, sir. Huh.
No.
Yes, sir. No.
Why isn't it? Is there any problem? You are watching this on mobile?
Yes, sir.
Okay.
Am I join again?
Yeah, try to join again. You can leave the meet once and join.
Now visible.
Okay. So always the stress axis is on the direction is taken on the y direction and strain is taken on the x direction. This is basically convention which was uh, across like various. It has been followed like so. Strain is taken as the quantity and stress is taken as an strain is as an independent quantity, which is of x direction and the stress is direction. Stress direction is y is the dependent quantity. So we have out the uh, Young's modulus. Young's modulus is basically, as I said, this is the slope of this line up to the point A, up to the proportionality limit. Uh, Whatever the slope of the line which we get is called as the Young's modulus. So here the thing is, uh, they have given uh, uh, till the point till the point elongation at 8.8 kilonewton. At this point, the load is 10.5 kilonewton at the proportionality limit. Sorry, 12.5. And let's say this point is some 8.8 kilonewton, just below the proportionality limit. And at this point, the elongation is given. Elongation of the specimen is given as 0.015 millimeter. So this is basically elongation. We have to get the strain from this. So strain at this point can be given as, let's say, epsilon. Uh, this point I'll just take it as small a. Epsilon a. You can write elongation by the original length. Change in length by the original length, basically. So elongation by the original length. So gauge length is, as you know, 50 mm. So we get the strain as 0.015 by 50, which is basically 3 into 10 to the power of minus 4. So this is the strain which we get. Then we know the strain which is just below. At point A, he has not given the uh, stress, but strain is like at small a and capital A, the strain is slightly varying. So I can use I can say that these 2 points have the same strain. Like when here I have given some drawn the diagram showing that there is some variation, but it is very small. So I'll consider this strain at point capital A is nearly equal to strain at capital A, nearly equal to, and Young's modulus is basically the slope of this point, which is tan theta. Tan theta is basically opposite side by adjacent side. So here the opposite side is the load, which is 12.5 kilonewton divided by 3 into 10 to the power of minus 4. So if I do this, I'll get 416 into you can say like 41666 123 666, yeah, 67 Newton per mm square. So this is the value of Young's modulus, and this is how it is calculated. This is basically the uh, slope of the line. And I hope yeah, I'll just check it. I'm just checking the answer. Yeah. Okay. So this I'll just directly. I just messed it up. Sorry. He has given the load and also elongation at that load. So why should I take uh, the other? So load at Young's modulus at this point, Young's modulus at this point here. So at this point, load is known, elongation is known. So I can directly use this only. I don't need to use 12.5, which is the proportionality limit. Uh, so up to this point only, I'll take this slope only. I'll calculate it. So we will get 266. Uh, yeah, this is the this is the strain. We get. This is the Young's modulus. We get. Load at that point. Sorry. This again we have to. This is the load. So this again I have to divide it by the load is given at this point. So I have to calculate the stress. I'm just messing it up today. Sorry. So stress at that point is sigma A is 8 into 10 cube divided by pi by 4 d square. So 8 into 10 cube divided by pi by 4. square. I'll get this 17.735. And now using this, I can calculate. So this I can Young's modulus, the value of Young's modulus, I'll get it as 235.78. That I can write it as 235.783 gigapascals. So giga means uh, 10 to the power of 9, 10 to the power of 9 gigapascal. So basically, I will get this as 235 because the stress is in Newton mm square. So I'll get this as 283 megapascal. So megapascal is also equal to Newton per mm square. So if I take uh, this like 235 into 7.83 into 10 cube megapascal. So mega is 10 to the power of 6, 10 to the power of 6 into 10 to the power 10 cube, which is giga. So 10 to the power of 9. So I'll get the Young's modulus. Sorry for the confusion. I have done now. So this is how we calculate the Young's modulus, the rough estimate. So if you know the load, you have to calculate the stress. If you know the elongation, you have to calculate the strain. Then you divide the stress by strain, you get the Young's modulus. And then we have to finally calculate the total elongation percentage or the total elongation percentage. So total elongation percentage is basically total elongation. They have given it as 10.6 mm, and the length of the specimen is uh, gauge length is 50 into 100. Change in length by original length into 100. So this is the elongation percentage. If we do it, we get 21.2%. Just check the answer again. So this is actually percentage. Total elongation is actually 3.05. So right, change in length by original length. So I'll get this as finally 6.1%. So this is the total elongation percent. So we have calculated the Young's modulus, and also we have calculated the total elongation percentage, and we have calculated the stress at the ultimate uh, stress point. So given the load is okay. So I have also done the uh, question of this strain gauge. I'll just do it because you know. So whenever we want to calculate the state of strain at a state of strain at a point using the strain gauges. We cannot calculate the state of strain with a single strain gauge. We at least need three strain gauges to get this. So there are various configurations of yeah, there are various configurations. Is it clear, right? Devashish, I have made a mistake here. This is 6.1.
Yes, sir.
I
Clear,
wrote,
clear, sir. Clear.
yeah, 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 okay. So there are various configurations of strain gauges which we use, which are called strain rosettes. So you take strain gauges in three different directions. This is called as a delta rosette, and there is also a rectangular rosette like this, strain gauges in three direction, and there is also a star rosette like this. So using this different configurations, we can calculate the state of strain. State of whenever I say state of strain, it gives the normal strains in two perpendicular directions and also the shear strain. So this is the state of strain, which is a for two-dimensional case. This is the state of strain, which is a 2 by 2 matrix. So a strain gauge, a normal strain gauge, when we use it will only give us the axial strain. It will only give us a axial strain in the along the length of the strain gauge. This is the length of the strain gauge, and this will give me strain along this length direction only. So axial. So I cannot. I can get only. So if I want the whole state of strain at particular point, I have to use this strain rosette and I attach at a particular point on the specimen. Though I am not attaching it at a single point because the distance between the strain gauge is very small. If you have seen the lectures, professor has shown strain gauges which are like very very small, and distance between them is very less. We can say that this is like a very small region, and you are calculating the state of strain at that point. So whenever we have, whenever we know the state of strain for a particular, if you know epsilon xx, epsilon yy, and we also know gamma xy, but we want to find out the strain in a direction which is making an angle theta with respect to x-axis. So you know epsilon xx, epsilon xy, gamma xy. But here we want to calculate epsilon n. So for this we have strain transformation laws. So strain transfer using the strain transformation laws, uh, we can give this normal strain along the uh, direction n, which is making an angle theta with the x-axis as epsilon xx cos square theta, epsilon yy sin square theta, plus gamma xy sin theta cos theta. This I can use the trigonometric properties like cos 2 theta is equals to 2 cos square theta minus 1. So if I write this cos square theta and sin square theta and sin theta cos theta in terms of two theta angles, so then I'll get this as epsilon xx plus epsilon yy by 2 plus after interchanging the terms, substituting the cos 2 theta and interchanging the terms, I'll get this. So I hope you know this trigonometric, like instead of cos square theta, I can substitute. Uh, uh, yeah. So you know, I hope I won't have to explain. So for a strain gauge, this delta rosette So this delta rosette is angles like this 60, 60, and 60, and this is strain gauge A, this is strain gauge B, and this is strain gauge C. So the strain gauge A is making an angle of theta is equals to 0 degrees with the x-axis, because this is lying on the x-axis, that's why it is 0 degrees. And strain gauge B is making an angle of 60 degrees. As you can see, strain gauge B, length of strain gauge B is making an angle of 60 degrees with the x-axis. And when you see this, strain gauge C is making an angle of 120 degrees with respect to the x-axis. So C is making an angle of 120 degrees. So theta A, theta B, theta C, 120 degrees. So assuming, let's say if I know xx, epsilon xx, epsilon yy, and gamma xy. So let's calculate epsilon A. That can be given as epsilon xx plus epsilon yy by 2 plus epsilon xx minus epsilon yy by 2 cos 2 theta. So here for A, this cos 2 theta is basically theta is 0, and gamma xy by 2 sin 2 theta, here also theta is 0 for A. So using this, I can get cos 0 is 1 and sin 0 is 0. So I will simply get epsilon A is equal to epsilon xx. So obviously this is natural. You can see that A is along the x direction. So straining in strain gauge A will give me epsilon xx. Then I go to epsilon B. The same thing plus this thing into cos 2 theta, which is cos 60, plus gamma xy by 2 sine 2 into 60, which is I'll directly write 120. And similarly, I'll take it as equation 1, this is equation 2. For epsilon C, you will get epsilon xx y by 2. I'll just write epsilon xx minus epsilon yy by 2 cos 2 into 120. Here the angle is 120 for C. Gamma xy by 2 sine 2 into 120 is basically, I'll just write it as 240. So basically here we know epsilon A, epsilon B, and epsilon C, but we don't know the values of epsilon A, epsilon B, and epsilon C are calculated from the strain gauge value, strain gauge are taken from the strain gauge measurements. So these are knowns. What we don't know here is epsilon xx, epsilon yy, and gamma xy. These are the unknowns. So we have three equations and we have three unknowns. If we simplify these three equations by substituting the value of epsilon A, epsilon B, and epsilon C, we can find out the values of epsilon xx, epsilon yy, and epsilon gamma xy. So these are three equations. If I simplify these three equations, I can say that epsilon xx is equals to epsilon A, and epsilon yy is equals to 1 by 3. I am just substituting the angles and simplifying this equation. Epsilon yy is equals to 2 into epsilon b into epsilon c minus epsilon a. And gamma xy can be given as 2 by root 3 epsilon b minus epsilon c. So epsilon xx, here in strain gauge A is given as, I'll just write the values. Epsilon A is given the problem as 300 microstrain. Epsilon B is given as 400 microstrain. These are the strain gauge measurements. 500 microstrain. These are the knowns. So epsilon A, epsilon xx is basically epsilon A, which is 300 microstrain. strain. So one component of the strain tensor is calculated. Then epsilon yy is 1 3 into 2 into V is 400 plus 500 epsilon C minus epsilon A, which is 300. So if you calculate this, you will get 2 into 900 minus 300 is 500 microstrain. Another component of strain tensor is calculated. Then I go to gamma xy. So gamma xy is 2 by root 3. This is 400 and minus 500. 2 by root 3. Just give me a second. Devashish, give me a second, please. I have just muted. Oh, I'm sorry. I had this guy whom I have to return something. He was not coming, so I had to take over. Yeah. So gamma xy, to do this calculation, I hope you can listen. I hope you can hear me, right?
Yes, sir.
Okay. So gamma xy is basically minus 115.47 microstrain. So we have calculated epsilon xx, epsilon yy, and gamma xy. This is how we calculate a state of strain. So this is for a delta rosette, which is making an angles like this. So there can be also a rosette like this, a rectangular rosette, which is having angle 0, 45, and another 60, and it can also be like this. So angles can be arbitrary, but we know the strain transformation law, which is this. So using this strain transformation law, we can calculate the state of strain uh, from the measurements of the strain gauges. So strain rosette will help us to give the state of strain at a point. So this is the question. So if you have any question to relating to that, you can ask me that. And
No,
first
sir.
thing I
Clear.
have discussed is clear. Okay. First thing I have discussed today is this. So whenever we have a uh, whenever we have to measure strain, so we can take a rectangular coordinate system. If the material, if the shape of the specimen is like a rectangular or kind of thing, you can take a rectangular coordinate system, which is basically x and y. So x and y, if we take, these are the values of state of strain: epsilon xx, epsilon yy, and epsilon xy. So for a rectangular coordinate system. But there can be some cases like if you take a plate with a hole, or a circular plate on which you have to calculate you have to give the state of strain. There we use a polar coordinate system where the directions are r and theta. R means the radial direction. As I go along the radius, that is a radial direction, and as I go on the circumference, which is theta, that is a uh, perpendicular. Sorry, theta is the circumferential direction. So this coordinate system can also be taken. So whenever you use this coordinate system, let's say the displacement along the radial direction is u, and here the displacement along the circumferential direction is v. So here epsilon r can be directly given as like similar like epsilon xx, which is dou u by dou r. Instead of x, we have r here, radial direction. But when we go to the circumferential direction, the normal strain is epsilon theta theta. Here we have this extra term u by r, which comes u by r, and like generally you can take generally like dou u by dou theta you can say, but this is a polar coordinate system. That's why we get this extra term u by r. Along with that, whenever there is theta, whenever you see theta, there is always r is present. So uh, so dou u by dou v by r dou theta plus u by r. And I hope you have watched the lecture how you get this using, like, professor has taken an element and he has described how we get that thing. And also we have gamma r theta, which is the shear strain. So this is similar to the red box which we have taken. This is similar to this, as I said, but theta and r are the independent coordinates which we take. So as there is theta, there should be r. But in addition to that, we have also minus v by r, the extra term. Yeah. This is the state of strain uh, definition in polar and as well as uh, rectangular coordinate system. So this diagram or this figure which you can see, this is giving a procedure to measure strain, which is called as a uh, three-dimensional image correlation. So three-dimensional image correlation, because it gives the state of strain measurements in all the three directions, which is x, y, and z. So the, whenever you have two cameras like this, arrangement like this, two cameras and a light source, uh, this will give me strains in the three dimensions. Okay, whenever we have only one camera, that is called as a two-dimensional image correlation. That will give me only the strain in x and y directions, and also the strain, which is xx, epsilon xx, epsilon yy, and gamma xy. So three-dimensional correlation will give me the entire 3 by 3 matrix. So in this, the specimen is coated with this speckles, like you have a white paint, and on this black dots can be seen. Initially, you take a image of the deformed shape of the specimen. As you apply the load, due to the deformation, this distances or the there can be uh, due to the deformation on the specimen, the distances between the speckles are also changed, and due during the course of the experiment, as you increase the load, you will be continuously taking the images. So after that, after taking these images, we will calculate the displacements u, v, w, and also we will calculate the displacement gradients dou u, dou uh, u with respect to x, u with respect to v with respect to y. All these gradients also we will calculate. So after doing these calculations on the computer, humanly it is not possible. All this processing is done by the computer using a lot of images, temporal data, which means time dependent. Like at some time instant, there will be image will be like this. At some time instant, image will be like that. Comparing all that, we calculate the displacement and the displacement gradient. If you know the displacements and the displacement gradient, so displacement gradient, if you have seen the last lecture, displacement gradient can be decomposed into two components. One is a rotational tensor and also a strain tensor. So using the strain tensor, we can get the state of strain at that point. And this image you can see. So one major advantage of the three-dimensional image correlation or the image correlation technique is you get the full-field strain variations. Full-field means on the entire element, on the entire specimen, I can get the strains. So using this technique, and this is also a non-contact technique. Like you are basically taking the images. So we don't need to paste anything on the specimen. So while pasting also, there are a lot of things like uh, uh, that is also very uh, specific job, that you have to take the strain gauges and paste it appropriately, and you have to make sure that the temperature effects, all these things are taken. So the advantage of this is basically that this is a non-contact thing. You take the images and you get the strains, and it gives a fulfilled measurement. Yeah. Yeah, photoelasticity. And photoelasticity is basically photoelasticity. It gives the stress variations. So photoelasticity is for uh, getting the stresses experimentally. Three-dimensional image correlation is basically for getting the strain measurements. So here you can see this. In this experimental procedure, we are doing three-dimensional image correlation on the one side of the specimen, and also we are also doing the reflection photoelasticity. So reflection photoelasticity is basically you have a light and you get a polarizer. Uh, uh, so polarizer is basically you are sending only one light in one direction. So I hope you have watched that lecture, a photoelasticity lecture. So light will be vibrating in different directions, but we will polarize it and only send the one direction light. And after that, because this is an opaque specimen, means light cannot pass through it, we can apply a photoelastic coating on the specimen, so that we will give, using that coating, you will get the reflections from the specimen. So using that reflections, you again put an analyzer. So analyzer again polarize it, and you will get beautiful fringes of the uh, stresses due to the applied load on the specimen. So this is reflection photoelasticity. So because the element is opaque, light cannot pass through it. We are taking the reflections instead of refractions of the element. So whenever the element is transparent, we will take the refractive photoelasticity. Here the reflection photoelasticity is used. So that's how uh, yeah, so using this, the basically we can calculate, we can get the stresses. Using that also we can get the strains. So we have strain and stress relationships. I think you are going to learn it in the next lecture. So that will also be there. Yeah. So that is what I had to discuss today. If you have any questions, you can ask it now. Otherwise, we can end it for today. Yeah.
Sir, I have a little question regarding the
Hmm.
stress in
Stress in.
invariant component, those I1 and I3.
Okay, okay, yeah. Hmm.
Actually,
What?
what is the physical significance of this stress invariant? Means, how
Yeah,
can we?
okay,
That's it.
okay. I'll tell you that. See, suppose you have some specimen or a material which is like this, and you apply some load, and some load you apply, and also there is some stress you apply, and also there are some boundaries such that material actually deforms. So if you apply load on a rigid body, it will continuously move. It will not deform. So if I apply load and there is some constraint, it will deform something like this. Let's say deform something like this. Let's say if I want to calculate the stress at any point on this material. So let's say this is point P. Let's say okay, I'll take a coordinate system like this, x and y. So if I enlarge this point, like this is a small point, if I enlarge this, zoom it, I'll take this as a small element, rectangular element, and on this you will have xx, yy, and you'll have shear strain, uh, what do you say, sigma xy or tau xy, whatever you can say, shear strains. Yeah. So this state of strain, I can write it like this, right? Xx epsilon. Only two-dimensional, sir. I'll neglect it. So this is the state of strain. But let's say you are changing the coordinate system. Changing the coordinate system, let's say instead of this coordinate system, I'll use this coordinate system like this, some x dash and y dash, which is having some angle with this, slightly rotated coordinate system. Okay. Then my element will look like this, right? And this is basically same xx dash, yy dash, and How? X dash y. System. Can you see this?
Screen not visible, sir.
Can you hear me?
Yes.
Hello.
Yes, sir. I'm. You are audible now.
Okay. So see, we have rotated the coordinate directions. Okay. So for this rotated coordinate system, the state of strain is this. Okay. The thing is, when we have a state of stress in one perpendicular direction, if we rotate it uh, to another direction, the values of this will change, right? So if you have stress in one direction, and if you want to if you stress on this plane is some, there will be some stress. If you change the plane, and which is making an angle some theta degrees with some other plane, there will be obviously the normal stress in this and normal stress in this will be different. So using stress transformation laws, we can go from here to here using the angle of rotation. So we are describing the state of stress at the same point here, but we are taking the reference coordinate systems in different directions. So inherently there should be something which should be same, right? Because the matrices are changing, the elements in the matrices are changing, but it effectively speaks of state of strain at that point. So there are some properties of this matrix, even if you change the direction of the coordinate system, that don't change. Those are called invariants. Here, the first invariant is sigma xx plus sigma yy, which is the principal diagonal, sum of principal diagonal elements. And here the second, in the second reference coordinate system, that is sigma x, the x prime plus sigma yy prime. Yeah, this is the first invariant. So whenever you strain the reference coordinate direction, the elements on in this matrix may change, but this invariance will remain same for that point. Yeah. first invariant is that. And here the second invariant for a two-dimensional thing is the determinant of this. So the determinant of this matrix and of this matrix will be same, xy and x prime y prime. This is the second invariant. So whenever when you go to three-dimensional case, first invariant is obviously sum of the elements, the principal diagonal elements. Second invariant is sum of the minors of the principal diagonal elements, and third invariant is the determinant of the stress matrix. Yeah, that is how. That's why we call it as invariants, because they don't vary. So whatever the coordinate system you take, you get a state of train as different, but the invariants of these matrices for any direction would be same. That's why these are called invariants. Invariants, which does not change with respect to coordinate direction, whichever you take. Did you understand?
Yes, sir. Understand now. So basically, this is
One second.
this is not.
Tell me.
So basically, when we change the reference code,
I'll just
yes, sir. Sir, basically, when we change the reference code or reference coordinate system, so the stress tensor are changed, but this due by this invariant we can get the stress tensor. Is it correct? Yes, sir. Okay, okay, sir. Understand, sir. Understand. Sir, no, sir. No, that's up to that's clear, sir. The next is after 1 week, na? You are going to do or any other? Okay, sir. Thank you, sir. Sir, another question is there, sir. I'm in now mechanical second year student. I am going to searching for the internship programs so you are going to do any research topic? Can I as a summer internship can I get, sir? Sir, but they are clearly mentioned that you are belong from the third year student means, but I am the second year. Yes, sir. Yes, sir. Because I'm fascinated about this photo elasticity and all these things. Because in my university, it's not there. If I'm got this chance to explore this thing or under you, if I work, maybe it is a great opportunity for me. Yes, sir. Because all of my friends are there. Not this visually they are not clear because we are studying all pen and paper because no visual things we can see. So how the stress pattern are generate all these things. So if we in our final year project, if we able to do these things, then it is very good for our juniors also, and it is a great learning for me also, sir. It's not a matter, sir. If in your under also, if you able to work, not a problem. I am able to. I'll do the work because basically I'm uh, interested to, sir, work under any research area, whatever. Sure, sir, sure. Photoelasticity is not a matter, means if in your under also it's okay, sir. Thank you, sir. Good night, sir.